So, start with some questions. Does anyone have questions on homeworks or anything to this point?
Could you do number 33?
Sure.
I kind of just played with my calculator, hoping to get a good number.
Yeah.
Which I kind of worked to answer, but wasn't the most successful one.
Okay. Yeah. Took me a minute to remember how to do this also. Grab that real quick. All right. Let's try to refocus here, folks. Especially you guys, my talkers in the back. Yeah, I know. They know. They know who I'm talking about. All right. So we're talking about number 33 here. So this says the West Michigan Whitecaps are trying to maximize their profits. 2 weeks ago, they found that if they sold tickets for $5, they sold 4,000 tickets. Last week, they sold them for $8 and sold only 3,000 tickets. How much should they sell their tickets for in order to maximize their profits? So, first thing to realize is that, profit is just going to be the ticket price times the number of tickets, right? And then we noticed that when we started at $5 and we added some amount, specifically $3, the number of tickets decreased by some amount, right? And that's the pattern we'd expect to see. As things get more expensive, we're going to sell less of them. So the problem with what we've written right now is that I have 1, 2, 3 variables in this. If I want to find a maximum in this function, I need it to be in 2 variables. So what I want to try to do is find a way to write y in terms of x. So the piece that I haven't used anywhere yet is that at $8 we sold 3,000 tickets. What I'm going to look at is I'm going to look at the rate that ticket sales is affected by price. So I saw that we sold 1,000 less tickets when the price increased $3, right? So this is the number of tickets sold, or I should say not sold, tickets lost or something, per dollar increase. So that is going to be what I need. So I can say then my profit is going to be, or my function for my profit is 5 plus x times 4,000 minus 1,000 over 3x. So for example, when x is 3, the cost of the ticket is $8, and I sell 3,000 tickets, right? So this checks out, like when I plug in my values for x, I get the points, right? When x is 0, I sell $5 tickets and there's 4,000 sold. which is the other data point. So this looks good. This looks like it's going to fit what I have. So all I need to do now is to plot this on my calculator. So 5x or 5 plus x, and then 4,000 minus 1,000 divided by 3 times x. My window, well, we're talking about x is like an increase from $5, right? So maybe we should have that go from like -5, that would be charging $0 for a ticket, up to, I don't know, 5 or 10 or something. $10 per ticket probably is pretty absurd. We'll make it $15 a ticket. I don't really know. Y is profit, so that's going to start out at 0 and go up to, I don't know, 5 times 4,000 is 20,000.
Yeah.
So I don't know, maybe I'll pick 30,000 as an upper bound. It's a lot of money for playing baseball games. So I have, there we go, there's my function. I'm concerned with the maximum on this because the question asked me to maximize this. I don't care that it's still going. That's fine. I don't give a rip about that. All I cared about was the maximum. So second trace, choose the maximum command. So right there is somewhere left at that maximum. Move my cursor. Right over here looks like good. That's somewhere right of the maximum, and then any guess is fine. So the x I get is about 3.5. So the price then was x, or 5 plus x. So about $8.50. And what do we make there? $24,083. Which seems like an awful lot of work to make an extra 83 bucks. Considering when we sold them for $8, we made 24,000. But $83 is $83, right? Somebody's gonna be mad if you leave that on the table.
Yeah.
What do you guys think? Is that okay? So again, the trickiest part was getting this thing set up. And this little trick that we did here to figure out a way to relate the number of tickets sold to the price increase was kind of the key to unlocking this thing, which was not obvious.
Yeah.
When Boyd came and asked me about it, I was like, oh, sugar, how do I do this thing again? And I sat here and made a mess out of it. I'm like, you know what? Ask me in class again tomorrow and I'll have it figured out by then. Because I was looking at it and I'm like, okay, so profit is price times tickets, and then what do I do with that? And yeah, it is. But that's it. That's the trick. Cracked it. It was too easy is the problem. Yeah. Just as an aside here, what assumption did we make when we did this thing that I highlighted in green?
You assume that people will buy tickets.
Well, that there was a linear relationship, right? Because what does that look like that I just did? It's like slope, right? I assume that there's a linear relationship between price and ticket sales, and that's probably not quite right, but it's good enough for this. It's going to be close. For reasonable prices, it'll be close. I'd expect at some point it just like drops off a cliff. But and then for cheap enough tickets or cheap enough prices, like the ticket sale is going to be constant because it'll just be a sellout, or you'd expect that anyways. Yeah. And that's a barring like, oh, the circus is in town. Everybody goes to the circus instead of the baseball, like stuff like real world concerns. Or the team is just downright lousy and you can't even give the tickets away.
Yeah.
But anybody else with questions that we want to talk about? Okay. Yeah, Dwan? 18? Sure. So it asks us to sketch the graph, including the vertical asymptotes, horizontal asymptote, zeros, y-axis intercepts. So we'll start with the vertical asymptotes. So there I'm just going to take the denominator, since it's already in a factored form, and set it equal to 0. So x equals -2 is my vertical asymptote. To find my y-intercept, I just plug 0 in for x. So there's my y-intercept. The zeros, I take the numerator and set it equal to 0. So I have that. Then my horizontal asymptotes or slant asymptotes. I need to look at the degree. So that's a degree 1 over a degree 1.
So these
Yeah, very good. So when the degrees are equal, it's leading coefficient of the top divided by leading coefficient of the bottom. That's going to be y equals 2. So go ahead and draw a little axis here. So at -2, I got my vertical asymptote. At 0, -1.5, and 1.50, I got those. And I got my my horizontal asymptote here. Well, the right side here, I can tell, has to kind of look like this. That's the only way to connect them and still follow the asymptotes. Over here, I need to figure out, should my graph be down here or up here, right? So the way I'll do that is I'm just going to check to see what's happening to my function as I get closer and closer to -2 from the left. So I'm just going to do this in my calculator. I'm going to use, since doing it numerically is kind of a hassle, but the calculator is really good at plugging stuff in. So I just type my function into y1, and then I'm going to do vars, y-vars, function y1. And I'm going to pick values that are less than -2 and see what happens as I get progressively closer to -2. And I notice that as I'm getting closer to -2, we're getting bigger. So we should be looking like that. And I'm all done. Yeah. Well, I did less than -2, right? Because things that are like a bigger negative number is less than right? Negative 2.1 lives over here. Negative 2.01, negative 2. Yeah, they're all less than negative 2, even though the number is like a bigger number, but it's like negative. So it's always, you got to be careful about it because it's easy to get yourself all turned around. Does that feel okay? Cool. And again, if you're like stuck and you're like, gee golly willikers, you can always just kind of like just graph it on a standard window and you should see what it should look like. You won't get the key features to spit out of it like we did here, but it'll at least like, oh yeah, okay. So I knew this piece, but now I can definitely tell what that's supposed to be doing to just confirm what you're seeing. Feel good? Okay. Oh, anybody else? Dwan. 9? Sure. Oops. So I'm not going to be doing any math, like any calculation to do this. I'm just going to be kind of looking at the picture. So the limit as x approaches 1 with the plus sign is talking about the right side of x equals 1. If I look at what the graph is doing there, it's pointing down. So that goes to negative infinity. If I were talking about the next one, that's going to be the left side of x equals 1. If I look at what the graph is doing there, it's pointing up. So that limit is going to positive infinity. If I look at when x is going to positive infinity, that's down here. If I look at what the graph is doing, it's following y equals 2. If I look at x approaching negative infinity, we're talking about that end of the graph. So there again, we're approaching y equals 2. So they're just kind of looking at the picture and writing down what the end behaviors that you're seeing. Yeah, it's way easier than maybe we wanted to make it, right? It's just a question of like, can I decode the limit notation to figure out like, oh, what arrow of the graph are they talking about? Right, because if I look at this, it's like, oh, there's like 4 arrows on the graph. Each of those is going to correspond to one of these limits. It's just about like figuring out which arrow the limit is talking about. You know what I mean? Like the idea is very intuitive. The notation's a little clunky to kind of understand at first, but like the idea is simple. Okay. Last call. Okay. So Friday we're going to do the chapter 14 homework quiz, just as a heads up. So that homework quiz is going to be like 14.1 stuff. So you should be able to find, like given some rational function, you should be able to find like vertical asymptotes and removable discontinuities, x-intercepts, y-intercepts, h horizontal or slant asymptotes, right? And then you should be able to do the other way. So if I give you like the vertical asymptotes and the zeros and the end behaviors and the x and y intercepts, you should be able to draw the picture that matches. So just, that feels like enough, right, for a homework quiz?
Yeah.
Now, I tried very hard when I wrote this to write these ones so that they're all using like a separate function, so that if you make a mistake in part A, it doesn't just like murder you throughout the entire thing. So I tried to separate them out into like skills where there's not a lot of error follow through. Also, just as an FYI, so they're like all separate situations. Okay. Everybody happy with that? All right. What do we have? We have like 10 minutes before lunch or something, right?
Yeah.
Okay. I'm going to do a little off book here today. So I want to talk about multiplying and dividing and then adding and subtracting of rational functions. So let's start with multiplication. And we're going to take us back to elementary school and just remind ourselves how we multiply fractions together. Let's say we want to do 18 over 20 times 25 over 81. Yeah, we want to reduce first and reduce as we multiply, correct? So I'm going to rewrite this as a prime factorization. So 18 is 2 times 3 times 3. 20 is 2 times 2 times 5. 25 is 5 times 5. 81 is 3 times 3 times 3 times 3. So I can cross out anything that's on the top with anything that's on the bottom. Everybody's okay with that? When they cross out, what do they become? Ones. So on top I have 1 times 1 times 1 times 1 times 5, or 5. And I have 1 times 2 times 1 times 1 times 1 times 3 times 3. That's 18. Because there's only 2 3s on top, so they can only cross out 2 3s on bottom. Yep. Yes, Bella?
For 18, why would you do just 6 times?
Yep. So you could have thought it as 2 times 9 or 6 times 3, but neither 6 or 9 are prime. So I just kept. I wanted to make sure I had prime factors, just so I didn't miss anything. And that's going to become even more important when we deal with rational functions. It's going to be really important that we have things as prime factors so that we don't miss anything, because it's much harder to look at 2 polynomials and tell, do they have any factors in common? Can't really tell, right? As opposed to like 18 and 81. It's like, okay, both the 9 goes into both of those. Right? Like we know that from times tables and stuff. Sure. Okay. So let's take a quickie example.
We just like factor all them into the x plus
Yeah, so that would be the correct first step. We want to start by factoring. So how do I factor x squared plus 5x plus 6?
x plus 3, x plus
Good. And then the denominator, x squared minus x minus 6.
2. X minus 3, x plus
Good. And we'll move on to the second fraction. How do I factor the top?
2. X minus 1, x minus
Good. And then the bottom,
3, x minus. Is it negative 1?
oh, shoot.
That's
Yeah,
awesome.
that's not possible. Let's fix that then. Just do that. And actually, yeah, let's do this. Make it that. Okay. So that should be
Minus.
plus 2 and minus 1. Okay. And from here, we can start reducing. Yeah, anything from the top can reduce with anything on the bottom. So we're just left with who says that's completely correct? Turns out it's not. So, and the reason it's not completely correct is very, very subtle. So for this to be completely correct, I should be able to take my beginning and plug in a value for x, and take our ending, plug in the same value of x, and get the same result, right? What happens if I plug, say, x equals 3 in here? Well, that's going to give me a 0 denominator here, which makes this undefined, right? If I plug x equals 3 in here, I get 6 over 5. Those two things are not the same, right? So I need to list a couple of values where like weird stuff like that can happen.
Yeah.
What values is that going to happen at? The weird thing I just pointed out? Obviously 3. Not multiples of 3.
3. No. Oh, it's all the denominator.
It's not the denominators, though. It's just the ones that we crossed out.
Oh.
It's the removable discontinuity idea. It's okay if we pick -2, because there we're going to get undefined. And over here we'd get undefined. And we're going to say undefined equals undefined. That's okay.
Yeah.
That's not technically true, but like for us it's fine. Is everybody okay with this idea? That's the general idea. Let's talk about division real quick. So for the sake of argument, I'm going to pick something like this. How do we divide two fractions? Going back to elementary school?
We take their 2 times whatever.
We turn it into multiplication of the reciprocal, right? And then it's the same problem that we just did in part, or the previous example, so I know that's already 5 over 18. That's how I did it so fast. I set it up to be the same example, so I didn't have to do it again. All right.
Do the same steps as multiply, but then just complete the.
Yeah, that's exactly what I would do. I'm going to do the same thing we did when we multiplied. The only difference is when I write the factoring, I'm going to do the flip at the same time. So I'm going to change that to multiplying, and then I'm going to do the x squared minus 9 factor on top, and the x squared plus 5x plus 6 on the bottom. Is everybody okay with what we did there?
Yeah.
I did the flip and the factor at the same time just to save the step. Because it's like a lot of writing and it's a pretty obvious thing to do. So my answer should be almost.
X equal 2. Plus or minus 2, plus or minus 3.
Yeah. Positive 1, or positive 2, negative 2, positive 3, negative 3.
Yep.
Keep it down over there.
What do you guys think? No big deal, right? Multiplication, division. Pretty straightforward. Go to lunch. All right, folks, let's get back together here and keep on going. So what we're going to talk about next is adding and subtracting. All right. So let's go back and talk about adding and subtracting fractions before we get into rationals. This tends to be the harder of the two skills. So let's go back to, once again, to elementary school here. And 5/6 minus 7/18 plus 11/24. Okay, great. So we need to have a common denominator. Here's the hard part. How do we find that common denominator?
See what the least common multiple.
Great. So you want the least common multiple of 6, 18, and 24. The easiest way to find that is to look at their prime factorizations. So each distinct prime should be in the least common multiple. So 2 and 3 need to be in there. And then I need the biggest power of 2. So that's 2 squared. And the biggest power of 3, 3 squared. So this should be 36. So if I look at these guys, what do I need to multiply 5/6 by?
Nice little 6.
Well, probably mean 6/6, right?
That's awesome.
And what is 6/6 really?
1.
Just 1, right? And that's why it's okay to do that, because we're just multiplying by 1. What do I have to multiply 7/18 by?
2/2.
2/2. And 11/24 will multiply by? Nope, you're looking at the wrong thing. Look here. You got to turn it into that. What do we need? Just a 3, right?
Yeah.
That's the easiest way to look at it. It's whatever that least common multiple needs to be. We just need to get the other factors in there. So now that we've done that, we can write this as a single fraction with a common denominator. Now, critically important question. Can I reduce at this step? The answer is no. Why not?
Because that's subtraction and addition.
Because it's an addition and subtraction problem on top, not a multiplication problem.
Sure.
So what should I do then?
Slow it on out.
I just need to multiply the stuff out on top. So 30 minus 14 is 16, and then 39 plus 16, or 33 plus 16 is 49. At this point, we can now check to see if we can reduce now that we've combined our like terms. But I cannot, so we'll call that our final answer. We'll leave it in kind of that factored form. Boyd.
So if you go back to the beginning, like, how did you know to multiply by 6/6?
Yeah, so I'm going to think about it this way instead of 6. I have 2 times 3. I need to make 2 squared times 3 squared. So I know I need 1 more 2 and 1 more 3. In the next one, I have 2 times 3 squared. I need to make 2 squared over 3 squared. So I need just 1 more 2. In the last one, I have 2 squared over 3. Again, I need to make 2 squared times 3 squared, so I just need 1 more 3. Does that feel okay? Again, if we think about everything in kind of its factored form, it's pretty easy to see what you need. And it translates really nicely to dealing with rational expressions, because it's really hard to go, okay, like if I have like x squared plus 3x plus 2, x plus 2, and x squared plus 2x, what's going to be the least common multiple of that? Yuck, right? And then like what would I multiply, x plus 2 by to get to that least common multiple? Yuck. But if I leave everything kind of in a factored form, it becomes pretty obvious. So let's do a quick example or two here. Okay, so let's say we have an addition subtraction problem like this. First thing I'm going to want to do is, I'm going to factor. So all the numerators are prime, but two of my denominators can factor. X plus 2 is prime, but how do I factor x squared plus x? Yeah, I can just take an x out. Good. So what's my least common multiple then for those three denominators? How many distinct prime factors do you see? I see an x plus 2.
Yeah. X plus 1.
I see an x plus 1. And I see an x. What's the biggest power of x? X to the first.
Yeah.
What's the biggest power on x plus 2? X plus 2 to the first. What's the biggest power of x plus 1? X plus 1 to the first. So this is my least common multiple, is just those three multiplied together.
Yeah.
So if I look at the first fraction here, what do I need to multiply x plus 5 over x squared plus 3x plus 2 by? Well, let's not write it that way. Let's write it as x plus 2 over x plus 1. So if I compare that to the least common multiple, what am I missing? The x. So I'll multiply the top and bottom by x. We'll do the same thing for the next fraction. Here I have x plus 2. Compare that to the least common multiple. What am I missing? X and x plus 1. And then we'll do it once again for the last fraction. If I look at the x times x plus 1 and compare that, what am I missing? X plus 2. Everybody okay here? So I'm going to have, let's just do this. Multiply the numerators out. Oops. I wrote, this is supposed to be a minus over there. Everybody agree that that's correct? You shouldn't, because I've made a mistake here intentionally. Ooh. Take a minute and see if you can find it. It's very sneaky. It's the number one mistake that students make when doing this kind of problem.
I found it.
So you missed an idea.
Yeah, that's correct. So what Bloom is saying is that really, when I distribute it, I should be distributing a negative 2x.
So then shouldn't that be a negative x?
Nope, because the negative only yes. Well, and the negative sign only applies to either the top or the bottom, right? If I have negative 1/2, that's like negative 1 over 2 or 1 over negative 2, but it's not -1 over -2. So it only goes to one place, right? And again, I'll make those kind of comparisons all the time when you guys ask me questions like that. I'll take it back to like just a regular fraction and remind you what the rules are so that it's like trying to connect it to things we already know how to do. That's the beautiful part about mathematics is like throughout all of high school, most of the stuff we do is still just relates back to these pre-algebra, like arithmetic ideas that we built out in elementary school. We're just kind of like generalizing, but all the rules are kind of staying the same, which is just amazingly beautiful. Okay, now we're good. What do we still need to do here? Yeah, we got to combine our like terms in the numerator. So I can add up those guys together and get 6x squared. And then I got to add up these guys together. That's going to give me 8x. And that's that. Okay. And then we should check to see if we can reduce this now, right? What do we need to do to reduce this? Excellent. And is there any reducing I can do here? Sure there is. The x's. Otherwise, we are good to go. Boyd.
But for that, this one, like with the last one, how did you know what to multiply the, like the x2 over x, or x2 over x plus 2, other ones?
Yeah, so what I did is I looked at what do I have in my denominator, and what do I need to get to? I have the x plus 1, and I have the x. I don't have the x plus 2. So that's what just comparing it back to that least common multiple, just like we did for the numbers, right? The regular fraction. It's the same idea. I want to point out one thing to y'all, is that we could have made this problem a little bit easier way back in the beginning. What do you notice about this fraction? The one I circled in orange. You could have reduced there. Why is that going to be a big time saver for us? Makes the least common multiple that much smaller. That saves us a lot of hassle if you catch something like that. Won't be wrong if you don't get the reducing, but that would have saved us a little bit of mess.
Yeah.
I just let it go because it was a nice opportunity to like come back to the end and show like, hey, you could have done this a little bit easier.
Yeah.
You guys want to do another one of these?
Sure.
Probably a good idea, right? Yeah. All right, so I have x minus 2 over x squared plus 4x plus 4 minus 2x squared plus x over x squared plus 2x, and then 7 over x squared minus 4. First thing I want to do is factor. So x plus 4 times x squared plus 4x plus 4 factors into x plus 2 times x plus 2. But for us, it's going to be really important that we write that as x plus 2 squared. And then x squared plus 2x factors to x times x plus 2. And I notice the numerator here could also factor. And I can reduce there, so let's go ahead and do that. Okay. So what's our least common multiple for our denominators here? If I look, I have x plus 2. And the biggest power of x plus 2 I have is to the second. And then I have an x minus 2. So that's my least common multiple. Helpful that we caught the reducing the x this time. That makes life a little bit easier. So, Boyd, I'm going to ask you, what do I need to multiply this one by?
X minus 2.
Great. I'm just picking on you because you asked me like how I did this like 3 times. So I just want to make sure that after we talked about it, you got it. Not trying to call you out for like you weren't paying attention. It's because you were paying lots of attention. Okay, what should I multiply this one by?
X plus 2 squared.
Nope.
No, is it just x plus 2 then?
X plus 2 and x minus 2.
Very good. Yes, sir. So I have one x plus 2, but I need a second one. And I don't have any x minus 2, so I also need one of those. And what do I need to multiply this last one by? X plus 2. All right. Oh, yuckarooskies, Kulik. All right. So I'm going to go ahead and FOIL here. Is it okay that I just did that quickly in my head?
Yeah.
And then I'm going to FOIL here. And then I'm going to FOIL again. And then here, just distributing. How's that look to you guys? It's wrong again.
We have to move that subtraction through.
Yeah, so that stuff all still needs the negative sign pushed through. I caught you napping. What's the worst part about these problems? There's a lot of write down, right? And just the ideas are not super duper complicated, but there's a lot of stuff to keep track of. When you actually do these in practice, what's going to become really important is organization, is that you're keeping track of where you're at in the problem, what you've done before, that you're writing enough intermediate steps so you can follow along to the next one. So go slow and be careful. All right, time to combine our like terms now. All right, so let's see. When we do that, I have negative 2x cubed. I have 0x squared, so I'm not going to write anything. 11x's and 22. Last step that I should do is check to see if I can reduce the numerator, or factor the numerator so I could reduce this thing, right? What do you notice about the numerator, though? It's a degree 3, so is it going to be something that I can easily factor? No, so I'm going to just not even bother trying. If it was squared, I would bother to check to see, but it's not, so I don't care. Good enough. What do you guys think? You ready to do some practice on your own? All right. I sure hope so. If you can't, don't strain yourself trying, okay?
Don't strain yourself.
All right. So this first sheet in OneNote, I have some simplifying problems, some multiplying and dividing problems, and I have some add and subtracting problems. Let's just say worry about doing the odds on these sheets. Since you have 2 sheets, we'll just do half of them. And don't worry about these like critical thinking questions at the end. Oops. Yeah. Okie doke. Okay, we'll stop here.